Hello, welcome to part 2. In part 1, I discussed general covariance, diffeomorphism invariance, and background independence, and how the three topics relate to each other. Here, I'm going to motivate the rest of the talk a bit before going into some mathematical details necessary to continue on. So we have those three notions, and I'd like to know if we can extend them into discrete space or lattice type theories. Why would we want to do that? Well, one sort of vague motivation is that quantum gravity is likely to be discretized somehow in space and time. Reasons to think this might be the case are the Bekenstein bound on entropy in black holes, the existence of the Planck length, maybe suggests that there's a fundamental cutoff in terms of energy or in terms of equivalently sort of length scale. So there may be a sort of lattice underneath things. It's one thought on how quantum gravity might proceed. So it's the case in like loop quantum gravity or maybe in causal set theory, something along those lines. Moreover, one might expect that GR's successor to be background independent in some sense. And now, as I mentioned in part 1, there's a lot of disagreement about how exactly background independence ought to be formulated. And so there's probably even less agreement about how we should extend that notion into discrete theories. So let's try and maybe address that. What background structure do lattices introduce? Do they introduce a lot? Do they introduce none at all? How would we judge a lattice theory as being background independent, or potentially of having the least amount of background structure if some background structure is required for a lattice formulation? I don't really know the answers to those questions, but the rest of this talk is suggestive towards their answer. Do lattices always break our continuous symmetries? Recall that we said that anything which breaks symmetries ends up counting as background structure. Is that true in lattices as well? I mean, what would it even mean for a lattice theory to be translation invariant, or rotation invariant, or Galilean boost invariant, or Lorentzian boost invariant, or diffeomorphism invariant? We'd like to consider lattice theories that have all those symmetries if possible, because our best theories do, and keeping with the symmetries has been a great way to move forward in physics. To answer these questions, it would be very helpful to have a notion of discrete general covariance, because as I motivated in part 1, general covariance is sort of the doorway into diffeomorphism invariance and background independence. It sort of supports those two topics, at least in the continuum context. Getting a handle on discrete general covariance will be helpful for us in answering these questions. So here is the analogy that I propose. And this is inspired by the work of Achim Kempf here. And there's a couple great references of his down here. Space-time could be simultaneously continuous and discrete in the same way that information can be. What a provocative title. So this is a great paper I would recommend, as well as this covariant information density cutoff in curved spacetimes. So this work can potentially be done in curved spacetimes, and Achim has done some great work on that. Very, very high up as an overview. The basic analogy is that coordinate systems will be analogous to lattice structure, and changing coordinates will be analogous to Nyquist-Shannon resampling. And general covariance is analogous to band-limited formulation. A generally covariant formulation, I should say, is equivalent to a band-limited formulation. Now, you don't know what any of these terms on the right mean, I expect. So this part of the talk will go through them. So we're going to review sampling theory now. So in the first part, again, as I mentioned, I've reviewed what's special about GR and differentiated these three concepts. In part 2 of the talk, I will now review Nyquist-Shannon sampling theorem. Not too mathematically and fairly informally. There are references which I'll include in the description if you'd like to find more information about these things. We'll talk about band-limited functions, uniform sampling, non-uniform sampling, and how this all works in higher dimensions as well. And then part 3, we'll put this all together. So onward with the mathematical review of the Nyquist-Shannon sampling theorem. A band-limited function is one whose Fourier transform has compact support. That is, it's a function fb of x, and the b subscript throughout the talk will indicate that something is band-limited. It's a band-limited function with bandwidth k, if and only if the Fourier transform of this function has support only for wave numbers with wave number k in magnitude being less than k, capital K, the bandwidth. So the Nyquist-Shannon sampling theorem tells us roughly that we can exactly reconstruct any band-limited function, knowing its values at a sufficiently dense set of sample points. Suppose that we know the function values fn, which is fb evaluated at xn, at some regularly spaced sample points, xn equals na. And suppose we also know that fb is band-limited with some bandwidth k. The following reconstruction then, fb of z is equal to potentially, I'm not sure yet, we'll figure it out soon, this sum here, which is these function values here multiplied by sinc functions. The sinc function here is sine of pi x over pi x, or pi y in this case, right? And the pi is just to normalize the thing. It is L1 normalized and L2 normalized. And the subscript here, n, shifts these by integer amounts. And the collection of all of these s and y, they actually form an orthonormal basis with respect to the L2 product. There's some mathematical details for you. But in any case, this reconstruction is approximate in many cases, but it is in fact exact, with no approximation, when our sample points are sufficiently dense. Here meaning that the lattice spacing A is less than this critical lattice spacing A star, which is equal to pi over k, where k again is the bandwidth. Let's see a concrete example of that. Consider this function fb here, which is constructed out of sines shifted by some amounts, it's squared and multiplied by polynomials. This turns out to be a band-limited function, and it has a bandwidth in particular of k equals pi. And so it has a critical lattice spacing of A star equals 1. So any spacing of lattice less than A star equals 1, we'll be able to reconstruct the function. We can discover fb exactly, knowing only its values at this discrete lattice with a spacing of 1/2, since 1/2 is less than 1. Here we know the function value at 0, at 1/2, at 1, at 3/2, and 2, so on, in both directions out to infinity. We know all of these values of the function, and from this we can recover the function exactly. And let me show you how that works graphically. To recover this function, what we do is associate each xn with a shifted and rescaled sinc function as follows. So here's a sinc function which matches at this particular lattice value, and notice that it's 0 at all of the other values. So we do find this sinc function shifted and rescaled as necessary, and then we do this for all of the points. So there's a sinc function associated with every point. What we do then is add these all together, and you recover back the original function fb with no approximation whatsoever. If we oversampled in the previous example, sorry, we did oversample in the previous example, we can recover fb from less data, knowing exactly its values at only fn equals na plus 1/3. So just the 1/3 is just an offset, just to show that generally you can have offsets. With a equals a star equals 1. So here we know it at 1/3, 1 and 1/3, 2 and 1/3, 3 and 1/3, and so on. From these, we again associate each point with a sinc function, shifted and rescaled as necessary, and add them all up. And from this, you will find again the original function with no approximation. So what I've shown you now, or what I've told you now anyway, is that we can reconstruct fb from any sufficiently dense uniform sampling. So far, I've always considered a sampling which is uniform, meaning it has an equal lattice spacing for each one. The magic of the sampling theory is that we can also recover fb from any sufficiently dense non-uniform sampling. This really is quite magical. Let me show you how that works. So consider this oversampling of fb with a equals 1/4, which is of course less than 1. So we do not need all of these sample points in order to do the reconstruction. In fact, we only need approximately 1/4 of them. Right? If we keep this one and drop, 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 keep, drop, 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 keep, and so on, and throw away or keep only every 4th one, then we could again have a uniform spacing, and we could reconstruct from just those. So we only need 1/4 of these. It doesn't have to be exactly that 1/4, which is so regularly spaced. It turns out that the samples that we drop do not need to be selected uniformly. The following non-uniform sampling will also work. What the process is to do the reconstruction from here is very similar to what before. The reconstruction functions are now more complicated, but in the end, we still have the function here being a function which is the sum of all these reconstruction functions times the value of the lattice at these locations. So in particular, these g's, what they do, the g1, let's say, for this lattice point, it matches the value, or sorry, g has a value of 1 at the lattice point in question, so that when we multiply it by this value, it stretches up to match here. So then this function is 0 then at all of the other lattice points. Okay, it's 0 at all of these. And this g function, actually, just from that information, if I asked you to write down a function with those properties, you would probably write down g correctly. What you do is you multiply polynomials like x minus this location times x minus this location times x minus this location, and so on. Multiplying them all together, that will give you the function if you when you normalize it in the right way. So it's really not too complicated, the function, what this g does. One thing to note, though, is that g here, the nth g, this is g1, let's say, so m equals 1. It depends on location, obviously, because it changes as we move around, but it also depends on the location of every other lattice point, xn. So you need to know what all the other lattice points are in order to reconstruct g. Another thing to note is that g does not depend on the bandwidth k. There's a unique function, there's a unique band-limited function which matches all of these points. Okay, so what we do is we find that g for each point, which is in general something like this. Note that all of these functions vanish at the same places. And then you add them all together, and you get back the original function with, again, no approximation. So there's the magic of non-uniform Shannon-Nyquist sampling. Remarkably, the same story is true in higher dimensions. If we consider this function fb, which just as an example I've taken to be the first Bessel function, j1 of pi r divided by pi r. So this is like a sinc function sort of in 2D, where r is the square root of x squared plus y squared. This function is band limited with a bandwidth saying that the square root of kx squared plus ky squared is less than k equals pi. In fact, the Fourier transform of this function is a disk supported over this area. So it's a uniform function over there. That's just a particular property of this function, which I think is nice. But any function which is compactly supported in such a way, whether or not it's uniform in its Fourier transform, will have the same sort of property. This is just an example. So all of the following figures are equivalent representations of this fb. Here, we just have the function plotted. So this is just the values of the function at the whole of the continuous space. This is that Bessel function. In an oversampled representation, recall that k was pi here, and so a star would be 1. That still holds up. That sort of analysis still holds up in 2 dimensions. So here we have it sampled at 0, 1/2, 1, 3/2, and 2, and so on in both directions. From these, multiplying by sinc functions in x and y and adding it all up, you recover this function exactly. So this has all of the information you could want about this function here. Here is a critically sampled square representation with a lattice spacing of 1, 1, 2, 3, 4, and so on in both directions. From this, you can also reconstruct the function with no approximation. Here is a rotated square representation. So we've taken these lattice points on this rotated square grid. This is, again, a sufficient way to represent the function. Here is a hexagonal representation of it. Again, from these, it's not going to be sincs this time, but there will be some sort of reconstruction function, which you can multiply by these and add them up and get the original function. Also, we can do a non-uniform sampling here. So it'll be much more complicated exactly how to do it this time, but there will be reconstruction functions, which multiplying them by all of these black points and adding them up will give the first thing, the band limited function again. Something to note here is that all we need is the values at these black points. And I've colored the areas around these black points to be the value, to be proportional to the value. Really, the data just exists at the black point. So let's keep that in mind as we move forward. So let's review. What's remarkable about band-limited functions is that they have a finite density of degrees of freedom. For instance, in this box, I might say that there's 100 degrees of freedom. And each degree of freedom is these black points. They can be adjusted independently of each other. I could move this one in some way and it wouldn't change any of the others. But, so we have this finite density of degrees of freedom, and we can localize each degree of freedom in a certain place, but we don't have to. Each of these degrees of freedom have no fixed or definite location. This is a point made by Achim Kempf in a number of his papers, but here's again a reference to a good one. So these are really quite magical functions because the things are discrete in some sense. They have a finite density of degrees of freedom, but they don't necessarily have much structure saying exactly where those degrees of freedom are that might count as background structure or break their symmetries. But more about that later. Moreover, we have near total freedom in how we can pick our sample points. So questions before we move on to part 3. In the comments of this video, please write any questions you have and I'll try and get back to you. One question that I recall from the PopGrunch talk, which this is sort of instead of, is that where do these functions show up in physics? Do people actually use band-limited functions for things? To my knowledge, band-limited functions are used in applied physics occasionally as approximations of things. Now, when you're listening to a song, let's say, or even the audio of this very video, your ears only pick up a finite bandwidth of frequencies. You only hear from a few hertz up to, I don't know how high the human ear goes, maybe a kilohertz or something. But there will be some range of frequencies which you hear. Now, so what that means is that if you took the actual audio in the room and replaced it with a band-limited version of that audio, if you ran it through a band-limiting filter, you wouldn't notice, right? And so this is how audio engineers sort of compress songs. You might think, oh, to actually record the realistic audio of some song, you might need to record exactly what the volume or the amplitudes of all the waves were at all the times. You may think that's what you need to record a song in full fidelity. But if you care about what the human ear will hear, you can cut out all of those frequencies outside of the audible range. Once you've done that, you can reconstruct the audio signal just from knowing the amplitudes at discrete time points. You don't need a continuous signal. And so this is how continuous signals can be made analog. When Achim here talks about could space-time be simultaneously continuous and discrete in the same way that information can be, it's this sort of information that he's talking about. The continuous profile of some band-limited signal has values at a continuum of time points. And it seems like there's information everywhere there. At least it has a continuous representation, but it also has a discrete representation. And so the question is if space-time itself could be simultaneously continuous and discrete in this way. This is really an excellent paper, which I recommend you read. So in these senses, band-limited functions are able to be used as approximations for physical systems. Another way to think about this, which isn't so physical, is think of the Gaussian. We use Gaussians all the time. Now Gaussians, the Fourier transform of a Gaussian is itself a Gaussian. And so it has support at arbitrarily high frequencies, except it's suppressed with an exponential tail. So if you cut off those tails and you don't affect things much by doing that, then you will have a band-limited function as your sort of approximated Gaussian. And you can do all of these techniques to that approximated Gaussian and get results which are approximately correct. But you may not be interested in how these things are used in approximations. Are there any systems which are fundamentally band-limited? As we'll talk about later in the talk, any system which is defined on the lattice is fundamentally band-limited. So any lattice theory, I can give it a band-limited representation. So all of those theories are band-limited theories. But you may be asking about like other things. So if you have what a band limit is doing is exactly cutting out frequencies above some limit. So in effect, it's like a UV cutoff. Now, of our best physical theories, they do all have UV structures which go out to infinity. They talk about infinitely high or arbitrarily high, I should say, wave numbers and frequencies. But we've never actually measured those things. The empirically confirmed content of any theory is always at finite frequencies, right? And so how do we, if we were to, say, be conservative and say, I don't know how these theories behave at frequencies above a certain point, let me just cut them out. They may be there, they may not be there, but my theory, my effective theory, let's say, will just cut them out. Now that could be a fundamental theory, and I'm thinking very seriously in this talk about what a fundamental theory which is band limited might be. But it is a thing that you can do is sort of just being conservative, saying, I don't know what these UV effects are, but certainly they're not relevant to my experiment. So let me cut them out, and I will develop an effective theory which is safe from them in some way. I'm not making assumptions about the UV structure which affect my local dynamics. Or sorry, my IR dynamics, I should say. Okay, hopefully that answers some questions about band limited functions, which you may have. Let me stop the recording.